Hello and good day to all of you. So today in this lecture, we are going to learn about the time frequency analysis in seismic data processing and also how actually it helps in interpreting our seismic data. It's a part of processing, but it's not a pre-stack processing or the processing which is done prior to having the migrated data, but it can be done into the last stage of processing. So it's more related to the interpretation as well as the processing. So let's look at the time frequency analysis. So what actually time frequency analysis are? So time frequency analysis is a strong method for describing a signal both in time and frequency domain. So the short time Fourier transform, which is also denoted as STFT, and Hilbert transform are the classical example of linear time frequency transform, which is actually used for time shift and frequency shift basis functions. And then also the short time Fourier transform and the wavelet transform are just two of many possible tiling of time frequency planes. So obviously, if we look at the data, which is normally we have in time domain, so we have to convert our data into frequency domain, and also it is in time section. So then we use normally for Fourier transform and Hilbert transform, short-term Fourier transform and Hilbert transform, which helps to interpret our data more better way, because now we have done all the processing before. Then after, when we are doing the interpretation, obviously we cannot go back and do the initial processing or enhance the frequency. But these type of analysis, which is time frequency analysis, which can be done at the spot to enhance our signal. So if you look at the functions, what are the distribution function of time frequency analysis? So as in the industry, we have a lot of function, and there are different ways to formulate a valid time frequency distribution function, and which resulting in several well-known time frequency distribution, such as short-time Fourier transform, as mentioned, and also it's include the Hilbert transform, and sometimes we have the wavelet transform, bilinear time frequency distribution, or it's also called Wigner distribution function, and sometimes we have some modified Wigner distribution function, and also the Hilbert hinge transform. So today the focus will remain on Hilbert transform, so we are going to discuss in detail. So what is actually Hilbert transform is? So if you look at the uh, Hilbert transform, actually it has been widely used to drive three properties of the seismic. So the first property of the seismic is instantaneous amplitude, or you can call it amplitude itself only. And the second property is phase, and third one is frequency. So these three frequency or three properties of the data, which can be derived from Hilbert transform of the time domain data. So what is the purpose of gaining these three properties? Actually, it is to detect the hydrocarbon detection. And the second objective to doing the Hilbert transform for edge detection, such as we have pinch outs, we have disconformity and conformities, these type of events. Then also sometimes we have to pick some events like anticline, syncline, where when we especially we are doing for the reservoir studies and we are doing the field development. So in that part, this Hilbert transform helps a lot, and some of other application as well. And however, the Hilbert transform results exhibit lower noise robustness and resolution. So the good thing is it does not increase the noise in the data, and also the resolution will be increased. We are going to look at some example as well on the real data. So the Hilbert transform is actually a linear operator that produces a 90-degree phase shift in a signal. So I mean the trace I mean we have the different traces and on different phase shifts. So it will produce a 90-degree phase shift of a signal and is a good first step in our expression of the phase. So in Hilbert transform, we also can apply to the post-tech seismic analysis, as I mentioned, and it can generate the analytical signal from which we can compute the standard complex trace attribute. So what are those attributes? So we have envelope, we have instantaneous phase, and also we can generate instantaneous frequency attributes. So normally if you look at the general use of this complex trace attributes or the Hilbert transform, actually it robust the it normally increase the resolution, and also there are some varieties of application of Hilbert transform. So let's look at the traces. We are talking about theoretical, so now we look at some example. So on the top left, which is denoted by A, it is actually a signal or a noise-free signal. So you see there is no noise in this data set. Once we convert or we look at the phase of this data, so when this B is showing the phase spectrum of these traces. And the third one is actually the Hilbert transform. So once we apply this data into Hilbert transform, so you can see the sharp edges, how it can be illuminated. On the right side is actually the same signal, but together with noise. So this is your input signal. And this is, again, we have the phase of this signal. And the third one is the Hilbert transform of the signal with the noise. So now we look at the real data. So now we focus on the phase and amplitude. So on the left side, we have the phase of the instantaneous amplitude data. So on the top, we have the amplitude, both example, and below we have the phase. So you can see how beautifully it has resolved, or you can see the edges of this reflector. It's already illuminated more. And even if you look at the faults, the fault in amplitude spectrum appears to be quite prominent. But in phase spectrum, we are looking for some other attributes. Also, if you look at the generalized Hilbert transform on the right side, and this one is your amplitude. But this application has been performed on a time slice. So in time slice, if you look at these features, so in amplitude, it does not represent the sharp edges of this channel or maybe this feature. But on the generalized Hilbert transform, so you can see a very beautifully, everything is clearly. So you can see this event or this anomaly is prominent here, but over here you cannot interpret this anomaly. So these are the different forms or different types of attributes or application we can do, and we can uh, apply to help the seismic interpretation as well. Moving to the coherence and curvature attributes. So on the left side, we can see it is the coherence application of the attribute on a time slice, and on the right side is a curvature. So over here, the coherence is normally used for discontinuity or this type of things. So you can see a lot of these events has been resolved. But on here, if you look curvature, so it is actually representing all the channels prominently. And obviously, it is a better than Hilbert transform, even the generalized Hilbert transform. So now we look at the complex trace analysis. So this is also one of the important tasks we have to do in processing or prior to the interpretation. So complex trace attribute analysis is actually a mathematical method to determine the seismic attributes, which include the reflection strength and also the instantaneous frequency. So how we determine these properties using Hilbert transform. So if you look at the complex trace analysis effect, a natural separation of amplitude from the angle, which is from frequency and phase, and then it allows the definition of instantaneous attributes. So the takeaway of this one that the using the instantaneous amplitude actually define the single lobe of individual wavelets. So if you have multiple wavelet and you have different lobes of the single wavelet, so it will define the each and every lobe of the individual wavelet. And also together with that, it will also use the instantaneous phase and frequency to resolve the reflectors. I mean, it has more power to because once you are using each lobe of the traces on the short gather data, or not short gather, but must be stack data or the pre-stack data, so you can have the better identification of the reflectors. I'm gonna show you one example of this one as well. So just keep in mind that this complex trace attributes helps to resolve the reflectors. So if we look at the types of complex trace attributes, so there are mainly three types of attributes we have in complex trace analysis. So actually what the purpose of instantaneous attribute, actually it compute based on sample by sample, such as we have the reflection strength, how strong is your reflection throughout the data set, and also the second thing is phase, and third thing is your frequency of the data. So now we look at the reflection strength in detail. So it represents the total instantaneous energy and its magnitude, and which is including the amplitude of the envelope as well. And also it is independent of the phase and related directly to the acoustic contrast. So here is the equation for that. So how we can calculate. So it's based on this is your reflection strength, and you can calculate by this expression. So what are the application of this reflection strength? So we can get the reflectivity such as AI contrast, then bright spot, one of the another application, such as we have gas accumulation in the subsurface. Then obviously if we are looking at the sequence boundaries such as unconformity, disconformities, or paraconformities, angular unconformity as well. So again, then we have the change of lithology, which can be also identified based on reflection strength. Let's say if we have some fault, environmental something, then we can identify that one as well. Also, if we look at the lateral changes of the fault, let's say how the fault is behaving in the subsurface, then we can look at this reflection strength, helps you to identify. Last but not least, we have the spatial correlation to the porosity and lithology. So these are normally we use the inverted data for that. So the second one is instantaneous phase. So what are the function? Actually, it emphasizes the continuity of the event because it's related to the phase. So where you have the phase change, so this means that your reflector is discontinuous. So it is independent of trace amplitude and related to the propagation phase of the seismic wavefront. So obviously the phase is based on um, the amplitude of the wave as well. So this can be expressed by this equation, and If you look at the application, so it is indicator of lateral continuity and discontinuity, because once you have the phase change, instantaneous phase, then you can look at the different discontinuity of the reflector, continuity or discontinuity. So, and the second application is detailed visualization of the bending configuration. And third one is sequence boundaries such as unconformity, pinch outs, faults. And also it can be used in computation of instantaneous frequency and phase velocity. So the third one is instantaneous frequency. So we have covered the phase, amplitude, phase, and now we are moving to the frequency. So actually it is time rate of change of the phase or the derivative of the arctangent function. So what it does actually affect the discriminators. It's a effective discriminator of the frequencies. So if you look at the application, so it's used for correlation tools in lateral direction. Let's say if your reflector is correlating with lateral direction, then it can change. And also the another application is hydrocarbon and fracture zone indicator by low frequency anomaly. And the main application is actually bed thickness. So if you have the high frequency, then you can resolve the thin beds. Probably if you have the low, then thicker beds. And also it can be used for chaotic reflection zone indicator due to the excessive scattering. So now we look at the examples. So this data on the top left is from offshore Australia. So this is the seismic data in time domain. So then we convert into the sweetness or combination image. So which is red shows the high sweetness and the blue shows the low sweetness. So over here you can see this reflection has been changed into different sweetness. Further we have change or we have apply on this data like just like instantaneous phase and as well as the frequency. So on the top left we have the instantaneous phase, and over here the blue colors, the dark blue, which shows the trough, and black shows the peak, and red is in between the shallow horizontal reflections. And over here on the left corner, on the down right corner, so we have the instantaneous frequency for the same section of the offshore Australia seismic data. So over here you can see the reddish color shows the high frequencies and the blue which shows the low frequency. So you can see how beautifully you can resolve, or you can see the reflectors and the discontinuity and continuity of this reflector. So this was the application from Australia. Then now we are moving to another data set, so which is again a real example. So this is our seismic data together with well logs. And on the right side, we have applied the instantaneous amplitude on this data. So you can see amplitude, how beautifully this, probably the indicator of high amplitude, has been resolved here. Then we have applied the instantaneous phase attributes. So you can see the continuity of the top of this reflector can be interpreted easily. Then we apply the instantaneous frequency to look at the thicker and thinner band. So over here we have the legend. So it can explain which are our thick reflectors and thin reflectors. So with that's all about the time frequency analysis, as well as some attributes which can be used using the Hilbert transform. Okay, thank you so much and have a good day too.